This is the video for data mining course, and I would like to continue to this topic about data transformation. So the data transformation, it is a function that maps the entire set of values of a given attribute to a new set of replacement values. It means we want to change old value to new values. So its old value can be identified with one of the new values. It means the transformation we want to transform. We want to change the value. Okay? We want to change the value or we want to convert the value. So what are the methods? We can do smoothing. Smoothing means remove noise from the data. We can do attribute or feature construction, means new attributes constructed from the given one. We can aggregation. This aggregation means summarization or data construction. We can do normalization. So it will be scaled to a smaller value or a specified range. We can learn later about the min-max normalization, z-score normalization, and normalization by decimal scaling. And there's also a concept about discretization. So we have the concept hierarchy. We will check the possible transformation methods that is already in this slide. First, I would like to explain about the data normalization. The normalization, there are some methods for the normalization, min-max normalization. So we want to change the old value into a new value by looking at the new minimum and the new maximum. For example, I have a particular value v and I want to convert it into a new value v prime. So I need to find what is the minimum of that array or that factors, and I need to find the maximum. I need to find the minimum, and we can subtract the new maximum with the new minimum plus the new minimum. For example, let income range between 1,000 US dollar to 8,000 US dollar, and it can be normalized to 0 until 1. It means the new minimum is 0 and the new maximum is 1. We can find the 6,000, okay, if 1,000 equals to 0 and if 8,000 equals to 1. So what is 6,000? So 6,000 will be somewhere in between 0 and 1. So we can put the formula like this one. 6,000, which is the value that we want to look for the new value, and the minimum is 1,000. Okay, so the minimum is 1,000 divided by 8,000, which is the maximum, minus by the minimum, which is 1,000, and we will multiply with the new maximum. The new maximum is 1. Okay, and then the new minimum is we subtracted here is 0 plus the new minimum. The new minimum is 0. Okay, and we will get the value 0.714. Then yeah, the $6,000 it will be transformed into 0.714. Now you can have another normalization. We call it z-score normalization. In the z-score normalization, we need to have the mu and the standard deviation. The mu refer to mean and the tau refer to the standard deviation. If we have a value v, we can subtract with the mean and we divide with the standard deviation. So we will get a new value which is v prime. Let mu equals to 5,000 and the tau is 1,250. Then the normalization for value 6,000 will be 6,000 minus 5,000 divided by the standard deviation, which is 1,250. Then we can get the value 0.8. So the z-score normalization is a kind of standardizing the numerical data. If we want to make the standard of this numerical data, okay, we can use the mu, we can use the tau, okay, and actually we can find the distance. Okay? We can find the distance between the raw score and the population mean in units of standard deviation. And as you know, okay, because it is about mean, there might be a negative value. Okay, so if it is negative, it means the raw score is below the mean. So if the x is less than mu, of course it is negative. But if x is higher than the mu, then it is positive. Okay. An alternative way is to calculate the mean absolute deviation. What is absolute? Absolute means you will make the absolute if x is less than mu, we do not care about the negative. So we will just keep it as a positive. Okay. So we have the function SF. It will be this formula. So the raw data or the raw score will be subtracted with the m. M is the mean. You can see this x1 f, x2 f until x and f divided by n. Okay, and what we can see this one is for every of the subtraction it will be absolute. So the standardized measure, it will be the z will be x, if this is the score, minus by the m is the mean or the average, divided by the sf. Sf is the standard deviation, but the standard deviation is using the mean absolute deviation. So using the mean absolute deviation is more robust than using standard deviation. So the standard deviation, okay, let's check with example. Okay, when we use, okay, we have this data. Okay, we have 5 data, and when we have this data, we will be able to calculate the total, which is 430, and the mean. Okay, the mean is 430 divided by 5. So this is the mean. Then if you do the mean square error or the common standard deviation, so this is the common standard deviation using the mean square error, you will have the value for every score. It will be subtracted with the mean, okay, and we will square it. So for square, it will be 1675 minus 86 square, it will be 121, and so on. And we will do the sigma. So we will summation this, the mean square error, and we will do the square root. Okay. SQRT means the square root. The square root of 370, which is the total on this one, divided by 5, then we will get a value 8.6. So the mean is 86 and the standard deviation is 8.6. Now, we can use the mean absolute deviation with the same data. We have the total and we have the mean. And what we are going to do with the mean absolute deviation is we just subtract the raw data with the mean, and we can get 4. Yeah, because we have this absolute, okay, because this is still positive, and the other, yeah, we have 75 minus 86, it will be negative actually, but we have the absolute, so it becomes positive. We will just do the summation for all data. We have 36 and we divide it by 5 because we have 5 data, and the result is 7.2. So once we have the standard deviation, we have the mean absolute deviation, we have the mean, now we can transform the data. What is the transformation? Okay, the transformation of the z-score, yeah, the 90 minus the mean, or 86, and then it will be divided by the standard deviation. So this is the value for the data number 1. This is the value for data number 2. This is the value for the data number 3. This is the value for data number 4, and this is the data for data number 5. You can see they're still negative, yeah, but yeah, it's still okay, because if you do with this deficient, okay, 8.6, so this value will be lower, and when you do with the 7.2 with the mean absolute deviation, it will be more robust. So some literatures mentioned that using this mean absolute deviation for the set normalization, it will be better in terms of the robustness. Okay, so this is the new value after we do the transformation. Now, there is also another kind of normalization. We call it normalization by decimal scaling. The normalization by decimal scaling, we have this formula, P prime, or the new value will be P divided by 10 power of J. So J is the smallest integer of that maximum of the new value. So we have this symbol, which is about the absolute. So the absolute of the new value and the maximum will be less than 1. So this is the formula, okay? And what we are going to look at for this normalization is based on the example. We have this data, okay? Minus 10, 201, 301, minus 401, 501, 601, and 701. So we will normalize the data above. The first is to find the maximum absolute value in the given data. So the given data is 701. Okay, among this data, the maximum is 701. So after we have the, we need to make it absolute first. You know, this minus 401. Yeah, but the 701 is still the highest one. And then we need to iterate J. Let's iterate J. It, it is we need to iterate J until it satisfies the condition. So what is the condition? The condition is, and the maximum p prime with the absolute will be less than 1. So we need to start j equals to 1. Okay, what is j equals to 1? So when j equals to 1, so the maximum is 701. Okay, and we will divide with 10. What is j? Is 1. So 10 power of 1. It means 701 will be divided by 10. So the result is 70.1. Because the condition should be less than 1. Is it less than 1? No. Okay. Then we go to the next j. So we iterate j until it satisfies the condition. So now j becomes 2. When j becomes 2, again we try to find the v prime. The v prime is 701 divided by 10 power of 2. 701 is the v divided by 10 power of j. J is 2. So 701 divided by 100, now it becomes 7.01. Is it less than 1? No. Okay, so this is still not the condition. The condition should be less than 1. So we go to the j equals to 3. When j equals to 3, it is 701 divided by 10 power of 3 because j equals 3. So the result is 0.701. Now, is it less than 1? Yes, it is less than 1. Then we will use the j equals to 3 as the value to normalize. Which is j equals to 3. So we divide the given data by 1000. Why it's 1000? Because 10 power of 3 is 1000. So every data here, it will be divided by 1000. After we have the value, okay, then you can see that this minus 0.01 is the result of normalization from this value. 201 is the normalization, and 0.201 is the result of the normalization from this value, and so on. Okay, so this is the result, or this is the normalized data. You can go to the orange. Okay. So in the orange, you can look at the, if you want to make another file, let's say I'm using the iris step, okay, and then you can call the pre-process. In the pre-process, you can see the left panel. Okay, the left panel contains some kind of widget like discretized continuous variables, continuous discrete variables, input using values, select relevant features, select random features, normalize features. So you can click this one and then move here, and you can see whether you want to standardize the data with mu equals to 0 and standard deviation 1, or you want to make it as a center with the mean equals to 0, or you want to scale with the standard deviation equals to 1, or you want to normalize to interval -1 until 1, or normalize to interval 0 until 1. Let's say you want to normalize this one. So you can look at the data. Now every data in the sepal length, sepal width, petal length, and petal width become a number between 0 until 1. Okay. So the next is about discretization. In the discretization, there are three types of attributes that we may consider. First is the nominal attributes. The nominal attributes means the values from an order set. Okay, we learned already in the first part of our lecture. Color, profession, so it is nominal. If it is ordinal, it is a values from order set. For example, military or academic rank. So lieutenant, captain, general. So it has some kind of level. The academic rank. So first is lecturer, 강사, and then 조 교수, 부 교수, 정 교수. So it is also a kind of order. And the other kind of data is numeric. We can have the real numbers, and the real numbers, it can be integer or the real numbers. So what we call as the discretization is we want to divide a range of continuous attribute into interval. Okay. So the continuous attribute is a number, but we want to divide it into some intervals. Intervals labels can then be used to replace the actual data values. It can reduce the data size by discretization. And actually, this is a kind of this the data for the supervised learning and unsupervised learning. For example, we can also use for the splitting. Okay? We can also use it for the merging. Okay? And discretization can be performed recursively on an attribute. And we can also do this discretization for other analysis, for example, classification. What we can look at the data discretization method, we have some data discretization method, for example, binning. Binning is a kind of top-down split. So you can look at the binning from the data distribution in orange. We can select the bin width. The bin width can be determined by the values. Histogram analysis. So the histogram analysis, what we already looked at the orange, it is a kind of example with the histogram, and it's also the top-down split. So we can also determine the bin width for this histogram. We can later do the clustering analysis. We can do the decision tree analysis. We call the clustering analysis is unsupervised. Okay, and then this is a top-down split or bottom-up merge. It can be both. For the decision tree analysis, it is a supervised and mostly it is top-down split. For the correlation analysis, this is using the chi-square. It is unsupervised, and usually we call it as a bottom-up. I think you already looked at this graph. We can see the discretization between binning and the clustering. So the binning, we can just look at the data, and then the binning will be in the middle of the data. But the clustering may have a kind of splitting. Okay? So the splitting value of this clustering or the centroid is better, is showing a better result than the binning actually. But the binning is more about the simple way to split the data compared to the clustering, which we need to use some kind of algorithm to make this clustering happen. So discretization by classification and correlation analysis, it can be useful for the classification. For example, the decision tree analysis. We call this is a supervised because we have the class label. So the class label is something for our decision, something it is a dependent variable. For example, I have the data and I want to decide whether it is a cancer or not. So there's a kind of tumor, we call it benign tumor and malignant tumor. The classification, we call it as a top-down approach, and it's a recursive split. Okay, we will learn more about this classification. We can also use the correlation analysis. In the correlation analysis, we will use the chi-square or chi-merge with the chi-square based discretization. We need to have the class information. So this kind of correlation analysis, it is based on the supervised and it is bottom-up merge. So we need to find the best neighboring intervals with those having similar distribution of the class or the low chi-square values, we can merge it. Because if the high, okay, if it is high, then it is more not not independent. So it's more dependent. If it is more dependent, usually we can use those two attributes for our further analysis. The merge perform recursively until a predefined stopping condition. We can also use the concept hierarchy generation to make a kind of split, okay? Or we can use this as the discretization. So this is a kind of concept hierarchy. Okay? In the hierarchy, we use a kind of uh, associated dimension in the data warehouse. So we have the drill up and roll up or drill down and roll down. What does it mean? Let's say if I have a cube like this one. So this cube contains of the time, item, and location. So I have the location as the city, okay, and I can roll up the city into countries. So for example, I have the city Paris, the city Toronto. So the city Paris, maybe there are some other cities again in this data, and I can roll up into a country which is France. Or I can drill down into some kind of details. For example, Q1, quarter one, this is time, and I can drill down into particular months. For example, January, February, and March. Okay. So with these two concepts, okay, so we have the concept hierarchy generation. We can discretize. This is the city in USA, so we can make more higher concept, or we can make like this one as a lower concept. So concept hierarchy formation recursively reduce the data by collecting and replacing low concept. Low concept means like numerical values. This is or age. Let's say I have the age is 25, 28, and then 35, maybe 50, or maybe 55 and 75 and 80. Then I can separate. For example, the person who are lower than 30, we call it youth. The person who are between 35 until 60, we call it adult. And the person who are more than 60, we call it senior. So this is also another concept hierarchy generation. So the concept hierarchy generation for nominal data, it can be used in the kind of address. So if you have address, uh, you have the specification of the ordering attributes explicitly at the schema level by users. So street is the lowest, and then city, and then state, and then country. Some specification of hierarchy for a set of values by explicit data grouping. For example, the city's Urbana, the city's Campaign, the city's Chicago, it is in the state of Illinois. The specification of only a partial set of attributes. So it means I do not use all those concepts. I use partially only street and city. So if we have this kind of specification, we can automatically generate the hierarchy or the attribute levels. So the attribute levels, in this case, I have street, I have city, I have state, country. So every data, it will be distinguished into four. So the first will be street, the second will be city, and then next is state, and then next is country. When you do with this automatic concept hierarchy generation, it means some hierarchies can be automatically generated based on the analysis of the number of distinct values per attribute in the data set. So the attribute with the most distinct values, okay, it means when the values are high, so it will be placed at the lowest level of the hierarchy. So the exception is about the time. We will not use the time as the concept hierarchy. But for this one, let's say the city, okay, sorry, the street, there are 600,000 distinct values. So it will be in the lowest one. And then next it goes to city, and the next we go to state or province, and then next we go to the country. Okay, what is discretization? We call discretization is we want to divide the range of a continuous attribute into intervals. Okay, that's correct. Next, can you mention some of the data discretization methods? Data discretization methods. Yeah, we have binning, histogram analysis, clustering analysis, decision tree. We can use the chi-square. What is the difference between equal width and equal depth? So in the equal width, we want to have the same width of the data. If we have the equal depth, we want to see the equal frequency. Okay. In the concept hierarchy generation, there are two concepts, drill down and roll up. What is the difference? Drill down means you will make more detail. For example, the Q1, you can see the January, February, March. Roll up. What is roll up? We want to make the higher level. For example, maybe we know the city in Korea, let's say Songnam. Suwon, Yongin. Okay, so we can just call the state like they are in the Gyeonggi province. So we want to up roll up to the higher level. Okay, that's the difference between down and roll up. So let's see in the orange how the orange can work with the equal frequency, equal width, and other things. So I will use the iris data set. Now let's see the discretization. The new orange show like this one. So in the orange, there are some options. In the discretize, you can keep the numeric. It means the data will be numeric, or you can remove it. There is another option, natural binning. So natural binning, what is natural binning? If you click on the natural binning, so the data will be distinguished into two. So the sepal length, for example, it will be distinguished into less than 6 and higher than 6. The sepal width higher than 4, less than 4. Petal length is higher than 5, less than 5, and petal width less than 2 and higher than 2. So it is a natural because it will create the desired number of pins based on the kind of median values, and the number should be integer. Or we can define the fixed width. How many width you want? For example, I want to have 2, or I want to have 3 width. So it will have a particular width. If it is about time, so we can make the time interval. So the time can be dedicated to years, months, days, week, hours, minute, and etc. Equal frequency. So equal frequency means the frequency when we already sort the data, the frequency will be the same if we split into two. Okay? If we split into two, then the frequency on the left and the frequency on the right will be the same. Equal width. The equal width means if we have the data here and if we want to split the data, we will check the interval, the maximum and the minimum. So the maximum minus the minimum, and then we will divide with the number of pins that you want to create. Let's say I want to create 2. So I have 2 pins, okay? Then it will be split into 2 like this. There's a slightly different between the equal frequency and equal width. When we do the equal frequency, the frequency should be the same, but in the equal width, maybe the frequency will not be the same because it is depending on the width. There's another kind of approach like entropy. So this is a kind of algorithm. I will not explain in detail. And we have a custom. Okay. For this splitting, you can make a different values. For example, I have set 5. Then every value will be split in the specific setting, which is 5. Okay, now you can just make a default as keep numeric. And let's say I want to keep all the values as a numeric, but for the petal length, I would like to change to equal frequency. So equal frequency k equals to 2. Then you can see that with equal frequency, the constraint will be less than 4.35 and greater than 0.35. Now, if I just do equal with, okay, because they try to find the maximum and the minimum, and we want to make two pins, so the value or the mid value is 3.95. Okay, then the condition will be like this one. If you look at the result, so the value from the sepal length, it is still numeric. The sepal width is still numeric. The petal width still numeric, but the petal length now it is distinguished into two, less than that value or higher than this value. So if you go to the data, now you can see now some data is higher than or equal to 3.95. So this is the result from the discretization. The opposite of discretization is continuous. The continuous means we want to make the data as a continuous data. So it is different. Okay? If we use the discretize, it is turn the continuous data into categorical data. But the continuous turn the categorical data into continuous data. Okay, so that's the difference. Of course, you will have question why we still have the numeric variables in this continuous. Okay, if you look at the function here, it is more related to the normalization. So the value will be standardized. The value will be centered, or the value will be scaled to the standard deviation when the standard deviation equal to 1. Or you want to normalize between -1 and 1, you want to normalize between 0 and 1. But if it is the categorical variable, then you will have different function. Whether you want first value as the base, or most frequent as the base, or we call it this is one hot encoding. So we will make it as a numeric, or remove if more than two values, you want to remove it, or you want to treat as ordinal. Okay, you know the ordinal means the value has an order, or you want to normalize ordinal. Okay. I will not explain one by one, but let's see only the one hot encoding. This is the most common category for continuous function for the categorical value. Once you have this, oh, I think we need to click this one, and then we need to select the one hot encoding. So what you will look at the columns. Now we have three columns. So the column one, it is about the iris setosa. The second column is the iris versicolor, and the third column is the iris virginica. So we have one. It indicates that this is the iris setosa, 0 and 0. Okay, so it is iris setosa, not versicolor, not virginica, and so on. If you go down, then you will see like this. This is 0, 1, 0. Then it is not iris setosa, it is not iris virginica, but it is iris versicolor because it is 1. Yeah, this is the way we can do for the categorical data, and we want to convert it into continuous data. So the value will be 0, 1, 0, something like this one. Yeah, you can try with other kind of approaches. For example, if you want to treat as the ordinal data, or you want to treat it as the normalized ordinal data. Yeah, if you treat as the ordinal data, then yeah, first is 0 and the other is 1 and the other is 2. Okay, so it is the easy way to uh, make the numerical attribute. Or you want to treat as the normalized ordinal. Yeah, this is 0 and 0 0.5, and then this is 1 because we have 3 values and so on. Okay, so you can just try with the other process. Yep, this is the layout from the previous version of Orange. I think you can just use the current version of Orange. So we already learned the data reduction. This is the time density reduction, numericity reduction, and data compression. And we also learned about the data discretization. It means we learn about the normalization, and we use the concept hierarchy generation. Okay, I think that's all that I can explain from this. Thank you, and we will meet on other video, or we will meet on the class. Have a good day.